All right, so today we're going to start our discussion in section 5.1 with addition and subtraction of integers. In particular, this chapter is our integers chapter. And in our integers chapter, we've got one section, 5.1, that's addition and subtraction, and then we've got one section, 5.2, that is multiplication and division. So you are very, very close to the end of new content material for our class. Yes, Gracie?
Not to get off at all, but will we be deciding the group stuff within the next couple weeks?
Yes, and I'm actually glad you asked because that way it'll be recorded and people can hear it as long as they're really in fall 2021 listening to this. We will select our section numbers and our project dates and everything next week. So I think it's November 15th. I think that's Monday.
Perfect.
I usually do it on the 15th. So yes, next Monday. Yeah, next Monday we'll be selecting our times and dates and so forth for presentations. I do have a bit of changing on the schedule to adjust with you, but I'll adjust it next time since we're already getting a little bit of a late start today. So you guys can know which days and which times correspond, and I'll post that inside of Canvas as well. So, okay, to start with, integers. Integers are positive and negative whole numbers. Your book uses a capital I for them. That's actually fairly uncommon. Most resources use the letter Z, and it's got a double line in the middle. They'll put the double line, like they double line it in. Do you remember when we did whole numbers and they looked like this? It's like that, and they do the double line on it. It's like that, okay? So they do the double line in the middle on the I, they do a double line in the middle on the Z. So these are integers. And we can start from the far left. I'm just going to put -3, -2, -1, 0, 1, 2, 3, ... I'm pretty sure the Z comes from Latin with the word integers. Do not quote me on that, but it's a different language. That's why the Z is actually what's used. And the reason I is not generally used is because we also have something called irrational numbers, and having the two-letter I's potentially could cause confusion, so you don't see I used. Yes, Emily?
Did you say that the I has a double line in the middle?
Yeah, it does. Can you tell it from here? Yeah. So it'll do a double line in the middle usually when you see it written. Or if it's in like your book, what they usually do is they just bolden things. Like they'll make the line in the middle look really bold. Whereas when we write it, it's hard to make things look bold in written form. So we usually double line things. Okay, so these are our integers. Okay, so I'm going to show you something with a chip model, but I've got actual manipulatives to use. So if you'll kind of just scooch your tables together a little bit, I'm going to bring around some chips for you. Okay, I think if I just draw on my screen and you have the little dots with you, I think we can do that so that I can catch it still on the iPad as we're working. The way that this works is that you have red and you have yellow, correct? And the best chip models have them alternate sides, which means you can use both of them, which is wonderful. So the side that is red is negative. So a red chip, let me get a red circle. Is a negative. These particular manipulatives use yellow, and the yellow would be positive. What you will often see is not yellow used, but black used for positives. And it has to do with its nice kind of throwback into a lot of your financial stuff being like you've heard the phrase in the black and in the red. Black means positive, red means negative. Black Friday comes into place. That word Black Friday has to do with the fact that that is the first day of the year that most companies are turning a profit. Yeah, for real. If you use a Microsoft Excel spreadsheet and you do addition and subtraction, it typically makes the numbers that are positive black, the numbers that are negative red. So that's what we'll see them used as. It doesn't matter to me what colors you use. They don't even have to be red and black. So if you have two different colors that you have, pens or markers or whatever, crayons, whatever that you're using, as long as you tell me what represents what, then you can use them. So you can use pink and purple if you want to use them. It doesn't matter. But here's the way this works. We have the number 5. So we do 5 positive chips. I'll use the yellows because yours are yellows. So I have 1, 2, 3, 4, and 5. Okay, there's 5 yellow chips. It doesn't really matter where they show up or how they show up, or you 5 black or 5 whatever. And then we need 3 negatives. So we're going to have 3 negative chips, so that's the red ones. Undo that. That wasn't what I meant to do. So we have 1, 2, and 3 negative chips. Okay, everybody good so far? Okay, so if you have a yellow chip and you have a red chip and you were to put them together, that's called a 0 pair. And those of you who've taken proportional statistical reasoning with me, we've seen that happen before. If you haven't, it's not a big deal. But a red and a yellow here combine together to be a 0 pair. So what does it mean? Well, it means that they add to 0. So you take 2 of these and they add to 0. You can mark them out. You can draw a line like you're removing them, whatever makes sense to you to say that they are no longer in existence because you've paired them up. And then what does remain here is the positive number 2. What do you think? Positive negative numbers can be very difficult for kids. I think I need to take these home for one of my 7th graders actually right now. He is still struggling with positive and negative stuff, and now he's struggling with positive and negative fractions. Not necessarily because of the fractions, but because of the positive and negative parts. Okay, it's something that's difficult for kids to get down. Now we're going to talk about what happens when we do subtraction with integers. That's just not going to be today. Multiplication with integers, right, positives and negatives, and division as well, and how that works. Some of them have really nice demonstrations with the chip model, some of them not so nice. But this is considered the chip model. What your book will do, just so that you're aware, is it will actually draw a circle around these, sort of like this. Oh my goodness, that was not what I clicked on. Sort of like this is the universe, right, and all the dots are inside the circle. They'll draw a nice circle. This is a sloppy one. And then they'll put the dots all inside the circle. So you can imagine giving your kids a circle placemat or considering the piece of paper as being in the circle, and then when you remove the 0 pairs, it just completely comes off the mat, right? So drawing those arrows out is why you see that happening here. All right, our next model, so you can slip the chips away, or you don't have papers to slip them into, just leave them sitting there. We may come back to them depending on how far we get today. It's called a charged field model. Now you're going to feel like, that's exactly like the other one. So it's very, very similar. Instead of using colors, right, so like the yellow and the red, it actually uses symbols. I wanted a black circle. So it'll start out just like the other one. I should have started out with a circle. That's how your book draws them. And what you do is it says that the 5 is a positive 5. So you put 5 like positive charges in here. They don't have to be in a row. I just did mine in a row. You can put it in there anywhere you want in there. And then it says I have 3 negative charges. So there's 3 negatives. So you're thinking more something kind of like when you do a positive or a negative charge to something instead of a positive or negative value to something. And you're still looking again for 0 pairs. A positive and a negative neutralize each other. They cancel each other out. So you take them in pairs and you remove them. A positive and a negative one at a time get removed. And then the solution, if you will, and I didn't draw the separate circle last time, but you could. The solution then is 2 positives like this still remaining in my circle, and the solution then is the number 2. All right, so far so good? We have 2 more models. I love the CHIPS model. Definitely a big fan of CHIPS model. I'm also a really big fan of the number line model. Those are my 2 favorites. The number line model is really nice because I feel like it thinks linearly, right? It thinks orderly, in an orderly fashion. So in this one, I have the number 5 and I have the number -3. So we start at 0 and we count over 1, 2, 3, 4, 5. Here's the number 5. And then this -3 says I go backwards 3. So in a very real sense, I went over 5 to here, like I skipped or jumped to 5. And then I have to go backward 3. So if I go backward 3, I'll actually sort of jump in the 3s, 1, 2, 3. I would land here. There's nothing special about me moving backwards in single jumps or a full 3 jump. It doesn't matter, but it was easier for me to draw the way I was looking at it. Is the number 2, so my solution would be 2. It's where I end. So this idea of moving forward and backward on a number line is particularly helpful. And I missed my phone call. Didn't feel it buzz or anything. Call back. Okay. Next one is pattern model. So the pattern model feels like a lot. It feels like a lot of writing, a lot of work. But we definitely have students in our classes who think in patterns quite frequently. So some of the different, autistic, things like that, where just this repetition, this pattern really fits in. This might be an option of something that someone in that kind of a category might really tend towards and like. The idea of the pattern model is to start with something that we already know how to do. So something like 5 plus 2. They're both positive numbers. I can add them, no big deal. It's the number 7. And then I create a pattern of taking that 5 plus something smaller. Well, 5 plus 1, well, that's 6. And 5 plus 0, and that's 5. Okay, so what we notice is that there's 2 patterns. Well, there's 3. These are always 5s. These always go down by 1. And this one always goes down by 1. Okay? So that's the pattern that we're establishing. The 5 will stay the same every time we do it. So I take the number 0 and I go back 1 and I have the number -1. Well, the pattern suggests that the next thing that happens from 5 is that I go down to 4. So I'm not really taking 5 plus -1 and I'm doing the addition. I'm actually looking at the pattern to establish that it should be a 4. Okay, so we've got a 4 here. The next one, 5 plus, and it's -2. Again, the pattern says that I should go down 1 from 5 to 4 to 3. And the last one, which is actually my problem, 5 plus -3, says I should go down 1 from 5, 4, 3, 2 and land at 5, 4, 3 and land at 2. Okay, I think we have time to do one more thing real quick. We'll just establish what absolute value is and we'll pick up there next time. So absolute value fits into this description because absolute value talks about the distances without paying attention to or considering signage values. So the absolute value of a number x, if x is greater than 0, is actually equal to x. Greater than or equal to 0. And then if x is negative, it actually ends up being that the absolute value of x is equal to -x. And sometimes that definition bothers people because it kind of looks like I just told you that something that's an absolute value equals a negative number. But here's what it actually says, the part that's in the box. It says that if I took the absolute value of, say, -5, y'all know what it's supposed to be. It's supposed to be 5. Okay, so I don't have a way mathematically to indicate remove the negative. Like there's not an operation that looks like remove the negative. Okay, I don't have that. So what the definition actually says is that I'm going to take the -5 and I'm going to multiply it by a negative. And in so doing, those two negatives cancel and give me a positive. So the reason that there is a negative x here is because when I take the absolute value of a negative number, that negative will cause the negative value of the number to cancel out. It adds in a second negative. So that's why the definition shows up that way. I recognize that it feels a little bit odd and a little bit awkward, but it works out to being everything that you know and recognize to be true. From a number line perspective, and I'll draw this and then I'll pause for today. If here's the number 0, what absolute values are really doing is they're asking for distances. So the absolute value of 5, -5, is 5 because this distance here is 5. And the absolute value of 5 is 5 because the distance back to 0 is 5. So absolute values measure distances back to 0. How far am I away? Okay, we'll pick up on a few questions about absolute values next.